So up to this point, we've talked about gravitational potential energy and kinetic energy, and the dependence on gravitational potential energy based on the height, and then with kinetic, the dependence on velocity, it being squared. Now, the gravitational potential energy for our purposes is going to be strictly on the y-axis, and that's of course because of the gravity. That's strictly on the y-axis. Kinetic energy could be from either axis, x or y. We introduced to you the idea of spring potential energy, and that's denoted with a subscript of s, and that's going to be 1/2 kx squared. Now, mind you, in some of the tests, books, quizzes, things you read out there, you will see that instead of PE, sometimes they use a big capital letter U. So just be aware of that. Now, our spring potential energy has a lot in common with the two other energies that we've discussed up to this point. Of particular interest is this variable K, which is a constant called a spring constant. It has units of Newton over meter, and it essentially is how springy is the spring. I know I'm not sounding very scientific, but the springiness of a spring is the spring constant. How stiff is it? How willing is it to go ahead and compress, to stretch? That's the spring constant. The spring constant first makes an appearance in what we call the spring force, which is the amount of force required to either compress a string or to go ahead and to stretch the spring. And depending on what you're looking at, there might be a negative, there might be a positive. It depends on where you pick your original equilibrium point and if you're stretching it or if you're compressing it. So let's consider a simulation of something called Hooke's law. And Hooke's law is this idea that the Fs, the force of the spring, is equal to K times X, where K is a spring constant, or it might be negative, and you'll understand better here in a moment why this is the case. We have a lot of things going on here, including an equilibrium point, this green dot right here, green dotted line, and you're going to see a couple of things happening. There's going to be a force that's going to be applied to the spring by this mechanical arm, which is going to be red, and then there'll be the spring force, the force that the spring experiences, as an opposite and equal reaction based on Newton's third law. Now, because this is going to be in equilibrium, it will also be first law. We'll go ahead and apply force. And as we do that, it displaces. Whoop-de-doo, big deal. But you'll notice something fascinating, that we have 100 Newton force applied. The spring experiences 100 Newton force, and this is why it's going to have that negative K value, negative Kx value, I'm sorry. And we have the displacement of 1 meter, and here's the spring constant, right? Notice that if I change the spring constant, it makes it more stiff. And if I get this to 1,000, I'm going to probably get, to 0.1. So this is all governed by essentially two variables. The spring constant K, which is this variable right here, and the displacement right here. Although in this case, the simulation doesn't let us play with it. It lets us play with a force instead. Now let's go ahead and explore the spring potential energy, keeping in mind this idea of Hooke's law with the force that the spring experiences. Now, there's a lot to absorb here, so you know how this works out. This time we're going to actually get to mess with the displacement. I'm going to get to see the forces being applied. We have the same spring constant as before. We can alternate that if we need to. Right, this is the force that's being applied, which means that there's a negative 60 force going the other way. If you were to go ahead and multiply this spring constant K with this displacement X, and if you were to then tack on a negative, you would have the blue arrow, which isn't showing right now, as the opposite and equal reaction, or the force that the spring is exerting. Now, what is this force that the spring is exerting? Because check it, if we were to go ahead and with the simulation release, right? If we were to release this, what does the spring do? It wants to return back to its equilibrium point. It wants to go back to here. What's going to make it do that? Well, that spring force, right? That Fs going in this direction. So as soon as I were to release this spring and this red force is gone, well, now we're in second law. Now we're not in equilibrium. And the spring wants to go ahead and return back to this equilibrium point. It's going to go a little bit past that, of course, and go back and forth until it comes back to this equilibrium point. But what's responsible for that is going to be that force that the spring is exerting in an opposite direction. Now, keeping that in mind, you have to recognize that there is some stored energy here. Otherwise, it wouldn't really be moving, right? So right now, it's in equilibrium. The velocity is 0. If we were to go ahead and release it, then all the stored energy becomes movement. It becomes velocity. It accelerates. And so then it becomes kinetic energy. So the kinetic energy in this case is not due to potential energy due to a height. It's actually due to the spring. And so that's what we're using this 1/2 kx squared. So all of this 1/2 kx squared, when I release this at this point, becomes kinetic energy 1/2 mv squared. I'm not too crazy for this bar graph. Let's look at the energy graph. This gets pretty fascinating. So you see that it actually forms a parabola. And that stands to reason because we have a squared term. Here is being compressed. So the applied force is going in the left direction toward the wall. We understand from nature that the spring is being compressed and wants to push against this red force. So in this case, we have 77 newtons going in this direction from the spring. I quite like to look at the force plot as well. And let me take the energy one off here. But notice that this is a force versus displacement. Here's our equilibrium. And then notice how it's a positive slope, now it's in quadrant 1, whereas when I'm compressing it, it's in quadrant 3. And what's fascinating is the energy, right? The energy, which is in joules, right? The spring potential energy is going to be in joules. It's going to be the area that is trapped between the slope of this line and the axis. Same thing when we go in this direction over here. It's going to be the area that's found in between the axis and the slope of this line. This kind of graph should remind you of work. The force versus displacement graph, the area of that graph is work. So you're seeing some similarities here. What can we do to increase this energy? Well, if we go ahead and increase the spring constant, that's going to require more force on our part. See, like if we had this back at 100, we don't require that much force to actually get it to move. But if this spring is very stiff, in order to be able to stretch it that long, we need to have be experiencing a greater force. And by experiencing a greater force and having it go through that same displacement, we're actually doing a lot more with the energy. Notice that our graph also changed there. There was less force required when the spring constant was a lot more loose. It was a lot easier to go ahead and stretch out or to compress. But as the spring gets stiffer, we require more of a force to be able to give it the same displacement. Doing this, of course, we recognize conceptually that if a spring has a very high spring constant, and we do end up displacing a certain amount of expected distance, that we're storing that much more energy because we're exerting that much more force or to be able to get it to that point. So here are a couple of sample problems. In these cases, we actually have springs that are hanging from the ceiling. Now, an ideal spring is hung vertically from the ceiling. So here's the ceiling, here's my spring. Boy, that's bad. When a 2 kilogram block hangs from it, now this is a 2 kilogram block, that's a mass, that's not a weight. So I'm not going to put an arrow, I'm not going to draw a free body diagram because I don't have a weight or a force, I have a mass. Hangs at rest, so there's an equilibrium, this is first law. From it, the spring is extended 6 centimeters. So you know, we have this equilibrium point right here. And from here to here, we have a displacement of 6 centimeters. Let me go ahead and change that ahead of time to meters to make it more useful for us. And then afterwards, we're going to go ahead and push up on this thing. So this is before. Afterwards, let me draw this in pink. Afterwards, we're going to push up on it and displace it a distance of 16 centimeters. So we have, afterwards, we're going to compress this, and like the block will be something like right here, let's say. Same 2 kilogram block. But notice that this time we went from this point right here all the way to this point right here, past the equilibrium point. And that was a total of 16 centimeters. Well, a distance of 16 centimeters, right? So that means it displaces a total of 16 centimeters, or let's see, let's put this over here, 0.16 meters. However, the way that it works with springs, we're not interested in the total displacement. We're actually interested in the displacement away from the equilibrium point, right? It's displacement. It's how far we've traveled from where we started. That's a technical definition of displacement. So this 0.16 is actually a distance, and what we really would need is a displacement from the equilibrium point to this point right here. Okay? Some technicality. So that's just a visual representation. We will first get to work by finding the spring constant. So we're going to find the spring constant based on this 2 kilogram block exerting a force on the spring and displacing it a certain amount. We're going to use Hooke's law for that. Now in this case, because we're looking for the spring constant, we can go ahead and ignore the negative. Or if you want to be really kosher about it, it's a negative kx, but it would be a negative f that's opposing it. What is responsible for this force? It's going to be that 2 kilogram mass. Actually, a weight, right? So we need to multiply it by gravity. We know the displacement from equilibrium in the first case, when the block is first applied, is going to be this much. So we divide both sides by 0.06 meters. That's going to give us a Newton over a meter. And if we put this in the calculator, we're going to get some nice long decimal, 326.66667. So this is the spring constant. This is how springy the spring is. And we're going to need that for the next part. When it asks how much work is being done, well, that's interesting, right? Because work has a unit of joules. And the work that the spring is doing is it's trying to push against the upward force that's pushing the block upward. So this work is really going to be due to stored energy that the spring has. So we have the spring potential energy that's going to come into play, and that's 1/2 kx squared. You know, just for kicks, just make it delta x squared so you can see what's going on here. And that's going to be 1/2 times the spring constant that we found earlier. But like I mentioned, this is how far away we are from where we began. So we could just find the distance between those two, and we would get what we need. Putting it into a calculator, we get that. However, there's a special phrase that we use in physics called work done. And so work done is going to be negative. And that is our answer to this problem. So this is quite a lovely problem that's actually really easy, but ends up being extremely deep, but ends up having the simplest of solutions. But let's go ahead and go through it all. So we have a spring hanging from a ceiling, and there's a scale next to it. If I put 100 Newton weight, which is a force, I get 40 for my x. If I put 200 newtons instead, I get 60. Question is, what kind of weight is going to be the one that results in a scale reading of 30? So if we put 100, we get 40. If we put 200, we get 60. What would be the 30? Well, we could take this from a very, very physics point of view and say, hey, I know this cool thing called Hooke's law. And it would be easy enough to find the k value, right? We can just divide both sides by x, and there's a k value. So for example, if we take these two, 100 divided by 40, well, that's 2.5. So we could just say, hey, our k value is 2.5. I don't even need this right here. We can take this 2.5, multiply it by 30, and the answer would be 75. Well, the interesting thing is, if you took that 2.5 and multiplied it by 60, guess what? It's not 200. It ends up being 150. So actually what we just did is not working out. For example, look what happens if I do the same thing with 200 over 60. I get a k of 3.33. So for some weird reason, this is not working out. And so now you're left scratching your head like, okay, that's kind of weird. Well, let me propose this very, very, very deep and simple point of view. You know, we have this table. Why don't we just graph these things? So we're going to make this be the force axis, and then this is going to be our distance or displacement axis. And let's go ahead and put some points. So we said that at 100, it was 40. And at 200, it was 60. And if I go ahead and form a line between those two, well, at what value do I have 30? Looks like 30 is at 50. So the answer is 50. So the unit for force is a Newton, right? And then over here we have meter. And so the slope of this line is a Newton over meter, which is the spring constant. So the slope of this line is a spring constant. The spring constant doesn't change its springiness or its stiffness. That's why it's called a constant. So regardless of what I apply to this, right? If I apply a 100 Newton force to the spring, it's going to displace 40. Or if I apply a 200 Newton force, it's going to go ahead and displace 60. So in this case, what would be responsible for a 30 meter displacement is going to be a 50 Newton force. And so our mystery weight or our mystery force is going to be 50 newtons.